Got a question for you. Consider the harmonic series. You may be very well familiar with this series. It's the series of 1 over n from n equals 1 to infinity, and intuitively you might imagine that as n gets really big, this 1 over n is getting really small, so we're going to be adding increasingly smaller values and this series is going to converge. However, as you very well may know, the series actually diverges. But why does it diverge? That's the question I'd like to get at today. And in my humble opinion, the best way, if not to really show why, but to really prove that this diverges, is with the integral test. And what the integral test basically says is that we can imagine this series as the summation of a bunch of rectangular areas. And if we do that, then we can correlate this series with an integral, make some connections, and make some conclusions based on that correlation. So before I get into why this harmonic series diverges, let's just sort of state what the integral test tells us. So the integral test says that if an integral f of x dx converges, then its associated series also converges. And by associated series, I'm basically saying that if your sequence a sub n, if you can find that by just plugging in n in that function for each term, then a sub n is going to equal f of n. Also, what the integral test states is that if the integral of f of x dx diverges, then the series of a sub n also diverges. And this is all contingent upon that function being continuous, positive, and decreasing. But how do we even get there? Well, if we take a look at the harmonic series, we can see how we got there. We can go ahead and look at its associated function. Its associated function is going to be f of x equals 1 over x. And we can go ahead and plot that out here, where this line here is f of x. Now imagine we wanted to find the area under this function using a left endpoint Riemann sum as a bunch of rectangles. And the rectangles might look something like this, shown here in green. And we could start adding up these areas of these rectangles to get our Riemann sum approximation. And if we did that, it's pretty basic. You can see that the height here, when at our x equals 1 value, is just going to be 1, right? Because it's the function 1 over 1 will just give us 1 for that height here. And the width of that rectangle, similarly, is just going to be 1. If we look at that next rectangle, it's going to have a height of 1/2 because we're at x equals 2. And the width is going to be the same, and that width is going to be the same for all of these, just like a typical Riemann sum with a constant delta x. And if we go ahead and look at another one, we'd find that that height is 1/3 and that width is also 1. And of course we can keep going like this. And if we wanted to add up all that area shown in the green, what we could do is just write it as an expression here based on these areas that we found. And since we're doing a left-hand Riemann sum, let's just call that L sub n. And we could say it's going to be equal to 1 for the area of our first rectangle, plus 1/2 the area of our second rectangle, plus 1/3 the area of our third rectangle. And of course we could just go on and on. Since this is a basic series, we could of course write this in series notation. So we could call that the sum from I equals 1 to n of 1 over I. We could also just imagine, if we are going to go out as n approaches infinity, we could just imagine that this, you can replace these i's with n's here, and that n is going to go to infinity on the top. So we end up with this series from n equals 1 to infinity of 1 over n, which of course is our harmonic series. So you can see we've sort of arrived at this harmonic series, but where we got it actually from this function of 1 over x, its associated function. So you can see that they're kind of related, at least in how we're trying to find the area here. But imagine we already found this area in the green here as this harmonic series. But what if I wanted to find this actual area under the curve starting at 1? It would look something like this, this area under here. So if I wanted to find that from x equals 1 all the way to infinity, that would be this integral, right? If we can say something about that area in the red, maybe that'll help us also say something about that area in the green. So let's just go ahead and try and find this area here, this integral of 1 over x from 1 to infinity. First thing we want to do is go ahead and notice that this is an improper integral because you got this limit up here at infinity. So what we want to do is change that to a proper integral. And there's a video linked here if you want to see just a little bit more on that process and why we do that. But doing that, we change it to this limit. And now we can just go ahead and evaluate this pretty straightforwardly. We just got to make sure and keep that limit in our next step, where we're going to take the antiderivative of 1 over x, which is of course natural log of x, and using the fundamental theorem of calculus part 2. So I'm just holding on to this limit notation for one other step. We've got the limit as b approaches infinity of natural log of b minus natural log of 1. So of course natural log of b, as b goes to infinity, that's also going to go to infinity. It's going to get really big. And this natural log of 1 just goes to 0. So we are left with infinity, which is great. We found what the integral of 1 over x was. However, that wasn't really what we were shooting for, right? We were trying to find what happens to this series here, this 1 over n. And like I said, they're not equal, but you can see that they're related in a sense here, because you can see the area in the green is going to be greater than that in red. So we can say that this series here, which is represented by that area, is going to be greater than that integral, which is represented by this red area here. So what we can conclude based on that is that series must also diverge. And that's basically what's shown up here. So that is the basic intuition behind the integral test. Again, not a rigorous proof, but you can notice here that the function that we used, 1 over x, that it is continuous, positive, and decreasing. So it matches the requirement over here. So I hope this helps you understand just a little bit better why the harmonic series actually diverges. But you can use this integral test for any series whose associated function you can integrate, assuming it matches all the criteria here. In particular, you can use it for series of the form 1 over n to the p. That's where we get our p-series test from. But again, hope this helps. Let me know, and until next time, take care.